Hi, welcome to Mathematics with Tom. This is Tom, and today we're going to look at the parametric equations of the line. So here's how this idea works. Normally when you graph a line, I'll make it fairly long here, maybe something like that, and normally we have our y-axis and we have our x-axis. But this time we're going to break our line. Instead of x and y being in the same equation, we're going to make two equations where this time each one of these is a function of time. So t is time. It can be in minutes or seconds or hours. It just depends on the application. So why would we want to do this? Well, let's start out, and I'm going to put a graph at maybe, let's start here at the point 2, 2. And what I'm going to do is I'm going to go over 2 and then over 3 and then up 2 and put a dot. And then I'm going to go over 3 more and up 2 and put a dot, and over one more time, over 3 more and up 2 and put another dot. And this is the line that I want to make. But here's what we're going to do. First, we're going to write out how the particle moves in terms as the x is concerned, and then as the y is concerned. So here's what this is. Notice that if we look at the x's, let's do it this way. When time is 0, x is 2. So that's my starting point. So let's do that in this pretty orange. So this is where I'm going to start. I want to start my line at 2, 2. This is the first beauty of a parametric equation, and that is that now your equations can actually have, your lines can have starting points. So they're more of like a ray instead of a line going off to both directions to infinity. This just goes, starts at a point and then continues out. Now, when time is 1, I need my x value to have moved all the way over to there. So let's see. Here's 2. So if I go 3 more, this is going to be 5. So when time is 1, x needs to be 5. And if we continue out 3 more units, then x is going to be 8, and then all the way out to 11. So when time is 2, x is 8, and finally when time is 3, x has to be 11. So notice this. Let's write this equation now. So I can write that x of t, let's write this, we'll write it over here, x of t, it starts at, when time is 0, it's going to be 2. So time is 0, it's going to be 2. And then after that, it moves 3 units for each 1 unit of time. And then, so that's how our x's work. We can do the same for the y's. So notice that the y's are also going, let's continue our table here. Our y's also start at 0. In time is 0, they start at 2. But then it moves up to 4. And then it goes up to 6. And finally, it goes all the way up to 8. So 2, then to 4, and 6, and 8. So the y's, my y's look like this. They start at 2 also. And then each time they go up by 2 for each 1 unit of time. And with that, now I have my line is broken up into x and y. Now often what we do is we would just write this as x instead of x of t. So x equals 2 plus 3t, and y equals 2 plus 2t. Now notice this. Let's just come back to our dots and let's connect them with this pretty melon color. And it looks like, if I was to sketch a line in here, that looks like about 2/3 to me. I'm not sure, but it looks about that. And also notice that my rise my rise on each of these is 2, and my run is 3. So it looks like if I was to write this line in slope-intercept form, I would write y equals my slope, which is 2/3 times x, plus my y-intercept, which is 2/3. So what I want to do is decide can you go from your parametric equations to this traditional form of a line? And here's what you do. So notice that we have it as y equals. So what we want to do is we want to take and put the x equation, solve it for t, and then substitute that into the y equation. So if we do that, we have x minus 2 equals 3t. Divide both sides by 3, so I have x minus 2, all of that divided by 3 is equal to t. And then we put that up into the y. So I have y equals 2 plus 2 times x minus 2 over 3. And let's clean this up. So this is y equals 2 plus, I'm going to write this as 2/3 x minus 2. Distribute to get 2 plus 2/3 x minus 4/3. And notice that 2 is the same as 6/3. So I'm going to write this as 2/3 x plus 6/3 minus 4/3. And look at that. There it is, 2/3 x plus 2/3. And so you can go from your parametric equation back to your standard form and notice that they do coincide and you get what you wanted. Now there's one more thing, and that is this. Notice that if we take x, so if I take the derivative with respect to t, because t is my variable in x of t. So this is going to be the derivative with respect to t of 2 plus 3t. So this is just going to be 3. And if I do the same with the y, so if I take the derivative with respect to t of y of t, well, this is going to be the derivative with respect to t of 2 plus 2t, which is going to be 2. And notice this. Now, normally when we talk about a slope, we talk about the slope as the derivative of y with respect to x. But let's see what we've got. Well, here our derivative of y was with respect to t. That was dy dt. Our derivative of x was the derivative of x with respect to t. And if you treat these like fractions, in other words, dy dx now is just dy dt times dt dx. And so that's how our derivatives work with our parametric equations. Thanks for watching, and in the next video we're going to take a look at another application of a parametric equation. Thanks.